This is Dr. Gomutanagam trying to give a series of short videos based on the request from a professional working in a reputed renewable energy company in India. It's an attempt to give an overview of the whole gamut of wind energy, wind turbine technology, and latest trends, and in addition, some extent the financial outlay and calculations, viabilities. Hope you would enjoy just having a quick overview in just 5 or 6 video clips. Let's start with wind energy. When it comes to wind energy generation, wind as a resource needs to be assessed. There are some basic technological concepts that would be useful, and most of the slides are a compilation during the National Wind Energy course run at National Institute of Wind Energy when I was the Director General. So we'll quickly go through the wind resource assessment fundamentals. As all of you know, a cyclonic wind like the Vardar cyclone in Chennai will be having high velocity. If you plot the time versus wind velocity, it will be a straight line here, and wind always will be fluctuating in a random manner. All of you would agree with that. And when you have such a fluctuating wind, if you take a time average over a 1 hour period, it will be about the mean. The higher velocities and the lower velocities will get cancelled, and finally you will come out with a mean value. That's called mean wind velocity or average wind velocity averaged over a given time. Say, let us say 1 hour. At the same time, if you take a short time averaging in the red box, shown in the red box, the average will indicate slightly higher value because the time averaging is smaller. So that's called gust wind. Suppose I take a 3-second time block as against a 1 minute or 1 hour time block. 1 minute means 60 seconds. 1 hour time block means 3600 seconds. So the blue one would be that kind of a large time block, and the short time averaging, that is within 3 seconds, is called gust wind. And the mean wind velocity varies along the height. As the abstraction effect reduces, the fluctuations become smaller towards the height. Okay, we'll see that in detail. There is an increase in mean wind velocity with height, and turbulent intensity is defined as the standard deviation of the wind velocity about the mean divided by the mean. A wide range of frequencies will be there in the fluctuations, as you can see. So Obviously, at this point, we have to remember wind is a vector. It has magnitude, speed, which is measured by these three parameters, and the direction is indicated by this vane, direction vane. So wind is a velocity. Wind velocity is a vector having scalar and direction. Let's now understand. We have said about the time averaging, the gust wind, and so on. And there's one more phenomenon called Van der Hoeven wind spectrum. You find here two peaks. This could be a 1 minute averaging peak, and this could be in days. Okay, this is called the cloud movement. Large-sized bubbles in the air, running in kilometers, hundreds of kilometers. Upper air circulation, lower air circulation. Macro meteorological peak. That is called this peak. And there is a micro meteorological peak, which may be somewhere around 1 minute here, average or so. And this would be towards the far end of it. You have a 3 second gust. If you look at the gust frequencies, it will be higher. Okay, and the macro meteorological peak will be very small, slower. This will be high frequency towards the gust on the right hand side, and the climatological changes would be in days or in seasonal. Okay, right. So what you should know, there is a spectral gap which is known as 1 hour to 10 minutes. The variation is not much. The energy in the wind is not much. So any measurement taken with the averaging time of 10 minutes and 1 hour would have a good representation of the wind in the area. That's why in wind energy calculations we use this 10-minute averaging. But at the same time, if you want to design a structure, you need the highest peak wind, highest energy content in wind, a 3 second gust or a 10 second or 15 second gust may be required, because any instantaneous high speed can stress the structure at that moment. So for structural design, we may require gust or high peak wind speeds. For energy calculations, 10-minute averaging is good enough. The more turbulent wind, the energy capture will be more difficult with wind turbines. We'll see that in the next view. And as this left-hand side slide shows, as the time averaging increases, okay, beyond 3600, this is hourly. If you take standardized as 1 hour averaging, 1 hour average hourly wind as a standard, then as the time averaging reduces, it will increase the wind velocity by this ratio. 3600 is hourly wind, ut is the gust wind speed given by the time averaging period. Okay, right. After all, wind is nothing but air in motion, motion of air relative to the Earth's surface. Free, clean, inexhaustible energy. Its intermittent source, of course. One day it may be calm, next day may be howling. It will vary from place to place and time to time. All this happens because of the differential absorption of just 2% of the solar energy in the Earth's surface, which varies in the ocean, in the surface, mountains, in the deserts, in the roads, habitats. So due to differential absorption of the 2% of the solar radiation on the Earth, there is a circulation, convection, that is that there is an exchange between sea breeze and land breeze. throughout the day and night. It's called diurnal variation. And such a convective oscillation in the atmosphere makes the air to move from place to place at different speeds, and that is called wind. Air in motion is wind. Right. All renewable energy, even the energy in fossil fuels, ultimately comes from the sun. About 1 to 2% of the energy coming from the sun is converted to wind energy, as we have seen earlier. And wind resource is a global wind system. Land heats up faster than water. Cool air over the water moves in. Warm air over the land rises. And water body takes time to get heated up, and it also takes time to cool down. And if you take the horizontal interannual variability of wind, that's over the years, how the wind pattern changes in a year, in a place. That's called interannual variability of wind. Normally it is plotted as a mean wind speed, annual average or hourly average or monthly. Annual average, diurnal variation in three elevations is shown here at the three different levels. Temporal and interannual variation, hourly and yearly. Wind speed variation can be counted, and the frequency of a particular wind speed happening at one point can be plotted as a histogram. And if by joining those histogram together by a continuous curve, you'll get what is known as a Bell spectrum or Weibull distribution or wind speed distribution. This gives you the probability of occurrence of a particular wind speed in a year. Normally, this is done through field measurements. And atmospheric boundary layer along the wind, along the height, how the wind varies, as we have seen earlier, it varies. A lot of high turbulence happens, more fluctuations towards the ground due to the obstructions and topography and orography of the surface. And as it moves up the boundary layer, the turbulence keeps reducing, and beyond some point, there would not be any further turbulence. Okay? That's called geostrophic wind, which may be 2 kilometers depending on the surface on the earth. And this profile, vertical wind profile, can be represented as a power law or by a log law. Using data from two elevations, measurement from two elevations, you can fit the power law coefficient, or you can fit the log law. Okay. Wind regime in India is influenced by strong monsoon circulations. Southwest monsoon during May to September brings the best winds. Wind speed during November to March is low, except in southern tip of Tamil Nadu. West windy sites of Kerala, Karnataka, Tamil Nadu, Gujarat, Andhra Pradesh, Maharashtra, and some more in Rajasthan and Madhya Pradesh. Right. How do we get power in the wind? The kinetic energy in the wind is called 1 by half mass into v square. V is the natural wind velocity. M is the mass flow rate, which is given by density rho into area, a circular area through which the wind blows, into velocity. area into velocity is the volume, rho is the density, that's the mass flow rate. Okay, it has a time domain, time. The kinetic energy, the mass flow rate is multiplied by V. This is called kinetic energy. Kinetic energy into m, mass flow rate, is called power. Okay. The other ways you can define power using translation of the force into velocity, or the torque into angular rotational speed. Okay. Torque into rotational speed. So we will see this little bit later in the technology part, how entry velocity V1 gets reduced to V2 after it passes through a wind turbine, because wind turbine is able to capture only a limited amount of wind energy. So the V2 will be less than V1. So the efficiency by which a wind turbine can capture energy, theoretically, theoretical maximum will be 16 by 27. That is called power coefficient, which is about 0.59. So in this presentation, we'll go to the main objective, is to identify potentially windy areas that also possess other desirable qualities for wind project development. What are the three key steps in wind resource assessment techniques? One is prospecting, large area screening, and field visits. Then validation, which is done through wind measurements, multi-level preferably, and data analysis at least for an year. Then micro survey and micro siting. Based on the measurements and large area scanning, using the orography or the topography, the surface roughness, the surface protrusions and valleys and hills, using that information, you should be able to identify places wherein you can plant a wind turbine, install a wind turbine to generate power. That part is called micro survey and micro siting. Let's see the prospecting part first. It is preliminary area identification, ranking of the possible candidate sites. Candidate sites is if you have three locations, like three places, you can rank the three places, which is the best one, first rank, second rank, third rank. And you can select the tower locations, development of monitoring plan, that is wind data monitoring, assuring the accuracy of measurements. So all these will be the prospecting steps. Preliminary area identification is objective is to determine or verify whether sufficient wind resources exist within an area to justify further more detailed site-specific investigation. So that this can be done through wind resource map lookup, use of existing wind data nearby airports, topographic indicators, that is the way the trees are bending, field surveys, flagged trees, and the way the grass is oriented, the way the sands are formed during the wind, accessibility, land use, obstructions, available land area for wind farming. Large area screening usually begins with a review of existing maps, analysis of climatology, such as terrain form, land use and land cover, and other logistics like accessibility, grid availability, and so on. Use of existing wind data in the nearby airport or where there is a continuous monitoring already taken place. Long-term reanalysis data from NSEP, NCAR, MERA. These are data points generated world over and kept in custody for the people's use for development of wind energy and wind pattern analysis and so on. Based on tower-based measurements, a wind speed map at 50-meter level has been indicated here. Wind power is measured, wind power densities given in the units like watts per square meter. Okay, the red indicates the highest, 200 to 250 watts per square meter. The orange one is 400 to 500 watts per square meter. So minimum 200 to 250 must be there for developing wind farms which could be economically viable to exploit. This is the wind speed map which is at 80-meter level. This has been now modified over the years. Topographic indicators could be the way the trees are bending can give you a kind of wind speed. This is normally used based on the tree pattern, complete throwing of wind. There are seven classifications where depending on the type of tree behavior due to the wind in the terrain. It's called Gibbs-Putnam Index of Tree Deformation. To look for physical evidence to support the wind resource estimate developed in large area scanning. Another purpose of the site visit is to select a possible location for a wind monitoring station, consistently bent trees and vegetation, example, or a sure sign of strong winds. Ranking of candidate sites based on the overall analysis. Objective is to compare areas to distinguish the relative development potential, like for instance, Theni, Nagarkoil, and Tripur, and so on. And that would be an analysis of accessibility, land use, proximity to transmission lines for evacuating power, potential impact on local aesthetics, if there are objections to the local community, the society, cellular phone service reliability for data transfers, potential bird interaction hazards. The WPD, as you know, the wind power is proportional to the V cube, wind velocity cube of wind velocity. Based on the WPD, wind power density, based on the wind speed, wind power density can be given for any site. So 7 different classes have been mapped in USA based on the available wind speed at 50 meter above ground level. So, and that is class 1 to class 7. And the power output of the wind rotor increases with the cube of the wind speed. This means that site for a windmill must be chosen very carefully to ensure that the location with the highest wind speed in the area is selected. And as you know, the wind slows down near the ground to an extent determined by the surface roughness, and that's called wind shear. The turbulence behind buildings, trees, ridges, etc. Then acceleration or retardation on top of hills, ridges, etc. Inflow wind, extreme wind, that is during cyclones or monsoon seasons. Sudden gusts, wake effects of structures or wind turbines. Turbulence and acceleration of ridge and obstacle. This must be studied very carefully with intuition and experience so that you do not locate a wind turbine in an area where there is stagnation, bubble, or where there is a highly disturbed flow. The flow inclination must not exceed plus or minus 8 degrees for any wind direction. Background turbulence, that is local turbulence, which would affect the wind energy generation. Higher tops of ridges may experience higher wind speeds due to effect of wind shear. And based on the prospecting, the large area scanning, and determination of the wind speed, measurable locations for wind mast locations, a validation must be done to assess the wind resource at a given site. That is done using a meteorological mast, which is today's standards, it's about 150 meters and so on, because large wind turbines are being deployed. In general, they are guide masts, which will have a cup anemometer or a direction vane along with the direction vane, or it can be a propeller anemometer or a sonic anemometer. There are several sensors for measuring wind speed and direction, like cup anemometer, which gives the magnitude of the wind speed, vane anemometer, which gives the direction of the wind speed, then vane ultrasonic anemometer, which works in the principle of sound detection and ranging, SODAR, okay, sound detection and ranging, or light detection and ranging, laser based LiDAR and LiDARs, SODARs, high tech devices which can be remotely operated, and hot wire anemometer, very accurate anemometer normally used in the wind tunnels. These are all instruments for measuring wind speed and direction. The pictures of that, one need not go into the details of these sensors. All of them are designed based on fundamental principles of counters, digital counters, or mass flow movement and directions and so on. But all of them are truly calibrated, and the calibrated constants will be used by you from the readings to log in the wind velocity and direction from these sensors. In this, the ultrasonic as well as laser or sound detection ranging instruments do not have moving parts. Okay, it senses wind velocity the way the ultrasonic rays are intercepted by the wind velocity that is passing through, while the vane anemometer will, based on its position, 3-cup anemometer due to the rotation, and so on. Remote sensing is one is through SODAR, sound detection and ranging. The other one is LiDAR. You can measure even the wind profile along the height without any mast. And The measured data must be analyzed for diurnal variations for each direction segment, okay, and to identify the predominant wind direction at any given site so that the orientation of the wind turbine can be in the predominant wind direction. And based on the time distribution, the frequency distribution can be plotted. And then we can use techniques for estimating wind resources depending on what kind of accuracy is required for numerical modeling to simulate additional data, either in synoptic scale or mesoscale or microscale.